All right, welcome back. So today we are going to discuss sequences which sort of can be looked at through a number of lenses. So one way we look at sequences is to view them as an ordered list of infinitely many real numbers. So ordered in the sense that there's a first one, there's a second one, there's a third one, and so on. So looking at this here list here, 1 is the first number in our list, 4 is the second number in our list, 9 is the third, and so on. So this creates an ordered list of numbers 1, 4, 9, 16, 25, and so on. If you're looking at that list, you might notice that each of the numbers in that list are sort of our consecutive square numbers. Well, that's not a coincidence. In fact, that's the list of numbers that is indeed listed there. Well, alternatively, we can present a sequence as a function, but a function for which only positive counting numbers can be input. So normally when you think about a function like f of x equals x squared, you could plug in whatever x you want off of the number line. You could plug in x equals 2.7 or x equals pi or x equals square root 3 or whatever. But whenever we talk about a sequence, we're talking about a function where you can only input positive counting numbers. Now, to signify this or to sort of denote this, we often denote the sequence instead of using the parenthesis notation for the input, we normally denote with a subscript. And instead of using x, which feels like it could be anything on the number line, we use n to sort of imply that we're only inputting natural numbers into this, or the positive counting numbers. And so a sub n equals n squared is an alternative presentation, in fact, of the exact sequence that was listed above. If you can only put in positive counting numbers, you can only put in 1, or you can only put in 2, or you can only put in 3, and so on. And if you would actually get out the exact sequence of numbers that was above, the 1, 4, 9, 16, 25, and so on. So you can think of an ordered list of infinitely many numbers as sort of the first number in the list being your A1, the second number in the list being your A2, the third being A3, the fourth being A4, the fifth being A5, and so on. So using the sort of functional notation that we have here with the A sub n, we'd essentially get a general form of a sequence as being the first number, the second number, the third number, and so on as A1, A2, A3. Just like with functions, if you want to distinguish one function from the next using f or g, you could distinguish one sequence from the next using a or b, something like that. Okay, we can also present sequences using recursive methods. So using recursive methods, this always reminds me of sort of like a for loop from computer science, but you sort of establish a first object. So we establish our first object to be 1, and then for all future objects, for all objects n greater than or equal to 2, we essentially establish a relationship between the next number and the previous. So an minus 1 here is going to be the previous number in our sequence, and here the next number in the sequence is just the previous number in the sequence plus 2n minus 1. And now this relation is going to hold for all n greater than or equal to 2. So it's almost like dominoes falling here in a sense. You set what the first one is, and then the first one determines the second one determines the third one, and so on. And so the way that this equation would manifest for given n's, if you let n equal 2, we would get a2 equals a1 plus twice n in this case for n equals 2 would be 4 minus 1. The next one, so notice here, A2 then would be determined by whatever A1 is. Actually, we know what A1 is, plus this 3 tacked on the end. Okay, so now A3, using this recursive relation, would be in terms of A2. In this case, A2 plus 6 minus 1, because when n is 3, 2n minus 1 would be 6 minus 1. So now A3 can be gotten from A2. A4 then could be gotten from A3, because using n equals 4 in this equation, we would get A4 equals A3 plus 8 minus 1. So in fact, if we want to sort of throw in the numbers that would result from this given situation, since we are starting with A1 equals 1, we could replace A1 with 1, and then we'd get, 1 plus 3, which equals 4. So now we would get A2 from A1. But now that we have A2, we could figure out what A3 is, because A3 is just A2 plus 5 in this case. Well, A2 is 4. We computed that previously. So 4 plus 5 would just be 9. So now we have A3 from A2. But now that we've got A3, we can compute A4 using our recursive relationship, because A4 is just A3 plus 7. but A3 was 9, so 9 plus 7 gives you 16. And in fact, noticing here how this recursive method presented the sequence of interest here, actually it presents the exact same sequence that we saw previously. So in this, sort of in these 3 dot points, we see 3 different ways in which we're presenting actually the exact same sequence, because the first number is 1, the second number is 4, the third number is 9, the fourth number is 16. It's the same sequence whether we're listing them, whether we're writing in functional notation, or whether we're writing in recursive notation, but it just demonstrates there's sort of 3 ways to linguistically present a sequence. Incidentally, you can also graphically or visually present a sequence, and here would be sort of a graph of this exact sequence we've been looking at, a sub n equals n squared. So when you'd graph here, you could sort of think of the inputs along the horizontal axis. So along the horizontal axis here, you essentially just have the positive counting numbers, and then what comes out would be up here. So here's sort of your n's going in, and here are your a sub n's coming out. Just like when we graph traditional function f of x equals x squared, we imagine the x is going in, and then the f of x is being the y coordinates that come out on a graph. It's a similar story here. However, where the graph is different in the form of a sequence is we can't put in anything between 1 and 2 or between 0 and 1. So whereas f of x equals x squared would be sort of this continuous function where you would not pick up your pencil everywhere along the way, a sequence is necessarily discontinuous in the sense that you have a point here and a point there and a point there, but nothing in between. So there's going to be a point at 1 comma 1 corresponding to the a1 equaling 1. There's going to be a point at 2 comma 4 because a2 is equal to 4. There's going to be a point at 3 comma 9 because when you put in 3 you get out 9 from the sequence. There's going to be a point at 4 comma 16 because when you put in 4 you get out 16 from the sequence. I don't have even space to put a5 on here because I've already capped out what my picture looks like. But yeah, you can see that the graph of a sequence is sort of, in some sense, related to the graph of the continuous function in terms of x, but is sort of more of a discrete object. There's just dots along the way, and well, that's the nature of that. So I'm going to pause the video here, and we're going to talk about some features of sequences that are particularly important to us within a calculus setting. All right, as far as we are concerned in calculus, perhaps the most important feature of a sequence is what we call the limit of a sequence. And so the limit of a sequence is really nothing other than the limit as n goes to infinity of the a sub n's. So, well, it could be b sub n's or c sub n's if you had a sequence that were given with a different name. But essentially, we're just taking a limit as n goes to infinity, which this is something that sort of calls back to knowledge that you acquired from your previous semester of calculus studies, whether it be in 141 or 132. So taking a look at these 3 examples, actually, I claim that we could determine the limit of each of these sequences. So what's the limit of this sequence? Well, it would just be the limit as n goes to infinity of 1 over n. And so, well, that limit, as n gets big here, right, the denominator gets huge. 1 divided by a huge thing is practically nothing. And the limit of this sequence here would be 0 as a result. What about the b sub n's? Equal to 2 to the 1 over n. Now, in principle, right, thinking of this as a sequence, you could plug in any positive counting number. So you could do 2 to the 1 over 1, 2 to the 1 over 2, 2 to the 1 over 3, and so on. These are essentially successive roots of the number 3. But what happens as n goes to infinity? Well, that would be determining what the limit of this sequence is. And the limit of this sequence, thinking about what happens here, 2 to the 1 over n, well, hey, as n gets big, that power goes to 0. So we would get 2 to the 0 or 1. So this limit would evaluate to be 1. That's, well, the value of the limit of this sequence. What about the c sub n's? We could determine the limit of this sequence as well. I mean, if you think about this sequence, imagining plugging in different natural numbers, different positive counting numbers. The first number in the sequence, c sub 1, would be cosine of pi over 1. The second number in the sequence, c sub 2, would be cosine pi over 2. The third, cosine pi over 3, cosine pi over 4, and so on. But if we want to talk about the limit of the sequence, we want to take a limit as n goes to infinity. And taking a limit as n goes to infinity here, note the pi over n would go to 0, and so this would limit to cosine 0, and cosine 0 is also 1. So incidentally, sequence a sub n had a limit of 0, sequence b sub n had a limit of 1, and sequence c sub n also had a limit of 1. Now, a bit of terminology relating to terminology which we have seen from improper integrals, but something that is equally relevant and actually in the same analogous context here. If the limit of a sequence is a real number, when I say a real number, like a number off of the number line, then we say that sequence converges. So in each of these cases, 0, 1, and 1, all numbers on the number line, these sequences converge. If we had a sequence whose limit evaluated to be pi, or whose limit evaluated to be -4, or whose limit evaluated to be 12.6, those are all real numbers. Those are all convergent sequences. On the other hand, should we be computing the limit of a sequence, and none of these sequences apply, I'll give examples here in a moment, but should we have a limit of a sequence being infinity, negative infinity, or non-existing, then we would say that sequence diverges. So let me pause the video, bring up some divergent sequences to keep us moving forward. All right, so here are three new sequences: a sub n equals n squared, b sub n equals ln 1 over n, and c sub n equals -1 to the n. And here are now three examples of divergent sequences. So let's take it byte by byte to see why each of these are divergent. So looking at this first sequence, if we were to determine the limit of this sequence, we'd just see what happens as n goes to infinity. But well, thinking about this here, as n goes to infinity, n squared also grows without bound. And so this limit evaluates to infinity. And as a result, then, we would say that this sequence diverges. So the sequence here diverges as a result of the limit of that sequence being not a real number. Infinity is not on the number line, and well, hey, that's enough of a reason for the thing to be divergent based upon our definition of the word divergent. What about b sub n equals ln 1 over n? Well, this is limit as n goes to infinity of, what would our limit be here? Our limit would be limit as n goes to infinity of ln 1 over n. Well, you'd have to kind of think about the ln function, the nature of it. I've actually sketched a graph over here of the ln function because, of course, when n equals 1, we'd get ln 1, which is 0. But then ln a half is going to be sort of further down this portion of the graph that's essentially asymptotically approaching minus infinity. Ln of 1/3 would be even further down this bit. Ln of 1/4 even further down. Ln of 1/5 even further down. In fact, as the n keeps growing, the input is getting closer and closer to 0. As the input gets closer and closer to 0, the output is getting closer and closer to minus infinity. And so here, the values are becoming negative without bound. The fact that the limit evaluates to be minus infinity in this case is a symptom of the fact that b sub n is a divergent sequence. So this sequence diverges because its limit is not a real number. Minus infinity is not a number off the number line. This last one, c sub n equals -1 to the n, is a nice emphasis of the subtle use of the word the in sort of our statement of a limit of a sequence. We're talking about the limit of a sequence. There can only be one possible number. Now, whenever you think about this sequence, this is sort of an interesting one here. If you just sort of sketch out a listing of the terms here, a listing of the terms C1, C2, C3, and so on, well, the first term is -1 to the 1, which is -1. The second term is -1 squared, which is 1. The third term is -1 cubed, which is back to -1. And then we go back to 1, and so on. So here we've got sort of the numbers -1 and 1 and -1 and 1 and so on. And the issue here is that we have oscillation leading to this limit not even existing, right? Because this limit sort of wants to be 1 and -1 simultaneously, which if we took a limit as n goes to infinity of -1 to the n, unfortunately, the result here just does not exist because, again, it would want to be -1 and 1 simultaneously, and that's well, there's nothing we can do about that. And so, as a result, this sequence diverges also. So, if I may, just to put a little bit of geometric context onto this situation, I'd like to show some visualizations of some of the sequences we just saw, just to hammer down exactly what we mean by a sequence being convergent or a sequence being divergent, and sort of what the limit of a sequence looks like visually. So give me 1 second to put this up. All right, so to sort of round out our knowledge of sequences and to sort of like bring to life the idea of a limit of a sequence, the limit as n goes to infinity of the expression of the sequence. Take the sequence a sub n equals 1 over n. As we determined previously, this is a limit that is convergent, or a sequence that is convergent. Its limit is 0, so this is a sequence that converges to 0. if you draw a graph of the sequence, you can sort of feel what we mean by convergence, right? Because this sequence never evaluates to 0, but gosh darn it, it gets really close, and eventually it gets as close as you'd possibly want to 0, in a sense. The further you go to the right, the closer the values get to 0, and in a sense, the values of the sequence are sort of like heat-seeking missile to the horizontal asymptote of y equals 0. What about b sub n equals 2 to the 1 over n? This was a sequence that we saw converge to 1. The first number of the sequence is 2 because 2 to the 1 is 2. The next number is the square root of 2, which is like around 1.4. Then you've got the cube root of 2, like what times itself 3 times is 2. Well, a number that's even closer to 1. The fourth root of 2, a number times itself 4 times equal to 2, is even closer to 1 than the cube root of 2 was. And these numbers are getting close to 1. So here also, like a heat-seeking missile, the points on this graph are sort of approaching the horizontal asymptote of 1. So in some sense, that's an intuitive way to see visually what we talk about with convergence. Because 2 to the 1 over n, just like 1 over n, never actually evaluates to the number that the sequence converges, but the values of the sequence get as close to 1 as you would ever hope to get. What about divergent sequences? Well, sometimes sequences can diverge because they go to infinity or negative infinity. Here's the example a sub n equals n squared, which sort of has this parabolic shape to it. And well, hey, if you just keep following the parabola up and up and up, the further you go to the right, you're never going to have a horizontal asymptote. There's never going to be a real number to which the sequence values converge by virtue of the fact that there's no horizontal asymptote on that function. What about minus 1 to the n? This was sort of a bizarre one. The sequence values were, oh shit, maybe I have this backwards here with this, this graph, because I think we evaluate to 1 at 2. But anyways, regardless, the point is, this sequence, whenever you look at its graph, it's sort of like a bouncing ball from minus 1 to 1 and back again. And in this instance, you'd almost think, oh man, there's like 2 horizontal asymptotes here. Right, but essentially, as far as the definition of a limit of a sequence goes, a limit can only be one thing, right? It's almost like whenever you have a jump in a function and the limit can't be both things and the limit doesn't exist in that case. This is quite analogous in the sense that the limit can't both be 1 and minus 1. And the limit certainly couldn't be 1 because the values are not sort of like a heat-seeking missile approaching 1, because every time the values are 1, the values then later are minus 1. So the sequence values are not getting arbitrarily close to 1 because every time the sequence values are 1, the very next sequence value is 2 units away from 1, which is quite unlike 1 over n, where the deeper and deeper you go, the closer and closer you get to 0. It's not that way here at all. So this is why we would have divergence in this case. So just a nice way to sort of visualize how divergence can manifest. And yeah, at that point, I think we've got a nice introduction to the notion of sequences.